We are honored to have Dr. Jacopo Iannacci with us today, and we sincerely appreciate him sharing his insight with our audience. In this webinar, Dr. Iannacci will be talking about the advancement of 6G and tactile internet technologies and the challenges in terms of hardware and software, as current hardware and software design methods are insufficient for 6G and tactile internet advancement. So this webinar emphasizes the importance of low complexity hardware components, particularly micro nano technologies, and proposes reinforcing hardware versus software separation and symmetry by drawing parallel with classical elements in nature. It introduced the VAF, water, earth, air, and fire micro nano technologies ecosystem as a framework. Leveraging these technologies essential for 6G and tactile internet transition and highlighting the key state-of-the-art research activities. At the end of, you can post your question in the chat, and at the end of the presentation, Dr. Jacopo will be answering your questions. So you are encouraged to ask as many as questions you want. Very briefly about Dr. Iannacci. So Dr. Jacopo Iannacci is a senior researcher with the Microsystems Technology Unit at Fondazione Bruno Kessler, FPK Italy, which is also my alma mater. He has received the MSc in Electronics Engineering and PhD in Information and Telecommunication Technologies from University of Bologna in Italy in 2003 and 7 respectively. He has more than 15 years of industrial and research experience in the field of MEMS, more specifically RF MEMS, that includes design, modeling, fabrication, simulation, packaging, and integration with sensors and networks. He has also greatly contributed to the scientific community and authored more than 140 scientific works, including international papers, journal papers, conference proceedings, books chapters, and one patent. In addition to that, he is associate editor of the Springer Microsystem Technologies and series editor of the IEEE Communication magazine. So without further ado, I would like to invite Dr. Jacopo to take this virtual floor. Please join me in giving him a warm welcome. Thank you. The floor is yours, Dr. Jacopo.
Thank you. Thank you, Kader, for the nice introduction, and good afternoon to everybody. Thanks for having me here. Okay, so let's get started. Thanks again. Good afternoon. So this webinar is about, as Kader correctly mentioned, is about, let's say, a sort of reformulation of the concept of hardware-based and leveraging micro nanotechnologies in view of 6G and future networks. This is the outlook of the presentation. It's split in 6 parts. First, I will provide a very brief overview of what 6G is today, is expected to be in the future. Then I will introduce a few conceptual tools which can help in let's say bridging the gap between 6G and future networks, which are very high complexity application frameworks, and micro nanotechnologies, which are actually hardware and physical technology for very simple components like sensors and actuators. And then finally, I will review a few examples which are available in literature and are in line with the future development of 6G. And I will spend a little more focus at the technical level on RF MEMS, as this is, let's say, my core activity here at FBK. I also, before starting, I also want to stress that There is some literature on these conceptual tools, and you can see here, let's say, the most important recent publications. In particular, the two IEEE articles are open access, so everybody can download it. And there is also a very recent publication in terms of a book published by River Publishers on these topics. So if you want to go deeper in this knowledge, there is some references. So starting from the brief outlook of 6G, 6G can be seen in two different ways. On one hand, it can be, let's say, in continuity with previous generations, including the current 5G, will mark an increase of KPI, of key performance indicators, and of performances, which is expected to be ranging from 100 to 1,000 times more than what 5G will possibly reach during his whole life. On a different perspective, more interestingly, 6G is expected to bring a lot of disruption in terms of how the network works, how the infrastructure is arranged, and so not only services and application. And this disruption leverages quite massively on the use of artificial intelligence. Here you can see just what it is expected to be in terms of increase of KPIs. Let's say I don't want to spend too much time on this. We can just focus on the average per user data rate, which is supposed to range from 1 gigabit per second in average of 5G to 1 terabit per second in 6G. Now, concerning technologies, there is a lot of discussion recently since a few years about 6G, and let's say the frame of reference is very complex. So an effort has to be taken in order to simplify the description of 6G in terms of key enabling technologies and whatever is related to it. And one effective way is to reason in terms of paradigm shifts, which is what is suggested in these papers here. So basically, it is possible to reconduct the disruption of 6G to certain wide areas, which are listed here in, let's say, in 4 different categories. The first one is a named scatter intelligence, which is related to what I was saying before on AI, because a disruption and the paradigm shift of 6G will be the use of artificial intelligence at each level of the network. Then the second shift will be concerning seamless coverage, then spectrum diversity and enhanced security. Now we'll see one by one these paradigm shifts. So concerning artificial intelligence, as I said, it will be exploited and capitalized at each level of the network, so from the core to the edge. And this will make possible to have step forth in the operation of the network, and also to solve very complex multidimensional problems which are difficult to address currently, in order to improve the efficiency and the resilience of the network at each level of it. So it will be possible, for example, to put together real-time data concerning the number of users which are connected in a certain area of the network, the energy available, the bandwidth available, and optimize this problem in such a way to have a network which is very adaptive. Concerning coverage, there is a lot of discussion now about this very diversified infrastructure, which overcomes by far the current concept of terrestrial network, which will make possible to have a real ubiquity of services. So to have the same KPIs which are maintained regardless of an end user is connecting from a very crowded metropolitan area where you have a lot of antennas, or in a rural or remote area. There is a lot of discussion about this integrated network, which features, of course, terrestrial infrastructure, but also flying objects, which are acting as hotspots, let's say from low-level flying objects like drones to airplanes to satellites, and also to have a coverage over sea with boats and ad hoc hotspots. Then, of course, if we discuss about increase of KPIs and of data, we have also to act on the frequencies. So the 6G is expected to be very diversified in terms of frequency spectra, which will be capitalized. And so ranging from the sub 6 gigahertz to millimeter wave, sub terahertz, and also there is discussion about the possibility to use light as a mean of communication, also in the visible spectrum, so with the so-called VLC, visible light communications. Finally, putting together all this discussion and recalling AI and the distribution of data and of intelligence to the edge, there will be a lot of concerns in terms of security. So ensuring security and trustability of data will be crucial. And for this, there will be the need of new technologies, ensuring, for example, security at the physical layer, so embedded in the hardware. And also there are some emerging technologies which can be suitable to improve the aspect of security, like federated learning for training of AI, blockchain, and quantum technologies. Okay, now I start to review some conceptual tool which will help, hopefully help in stepping from the very large picture of 6G at the application level to micro and nanotechnology, and to, let's say, craft a role for such a technologies within so complicated and high-level scenario. The first one is described in the book that I mentioned before, and is named the core versus edge model. This is basically an empirical description which somehow wants to stress the way the telecom standards evolve from 1G to the current 5G and how they are expected to evolve in the future. This is basically, let's say, the discussion of this core versus edge model is focused on the distribution versus centralization of the network. To do so, per each generation, three classes are identified: data, services, and physical infrastructure. Is a very visual description of the standards. So basically, let's say, data, services, and physical infrastructure are, let's say, tilted towards the edge or towards the core, with arrows which can be thicker or thinner depending on how much these data are to the edge or to the core. Let's say that the central point does not represent a specific point of the infrastructure, but the arrow just indicate in the qualitative way how data are generated and are traveling more close to the edge or to the core. So with 1G, the situation is quite easy because the data are basically voice conversations and the services are just calls. And the physical infrastructure is made of radio towers, which is, let's say, towards the core of the network, and mobile handsets, which are the let's say, the mobile devices making possible voice conversation. Now here, I just keep the 2 and 3G because they are, let's say, not so, they don't bring so much information, additional information compared to 4G. You can see, on the other hand, that 4G is much complex because, let's say, there is a more scattering of the physical infrastructure, which includes network hand and human end user hand. Because also machine user hand, because with 4G it was started to be incorporated also the concept of machine-to-machine communication. What is relevant to see is that in 4G, the tilting towards the core is much more pronounced. This means that actually 4G, as it was already starting with 3G, is a more centralized paradigm rather than previous generation. With 5G, this effect increases. Of course, it's also the scattering of other devices is more tiny because we have also wearables, implantables, and so on. If we then step to 6G and future network, we see that there is a sort of inversion, because we still have quite an important, let's say, traveling of data towards the core, but the distribution becomes more prominent, as you can see with these thicker arrows towards the edge. So if we compare the 1G with 6G and future networks, we can see that they are quite similar in the sense from a, let's say, conceptual point of view, because they are very distributed networks. Okay, so basically this means this is, let's say, this model is just to grasp the concept that what will be after 5G, for many reasons that we will also see later on, cannot be a purely centralized network. So it cannot be just developing towards the core, because the amount of data that will have to travel back and forth will be simply unmanageable. So 6G will start a sort of return to distribution, so to the edge of data, which will be generated locally and used locally, stored and computed locally, still keeping, let's say, orchestration with the rest of the core, so still working as a whole. Okay, the subsequent conceptual tool is called the Identifying, Define, Deriving methodology, I2D. This is also discussed in the book. I will just stress the main concept of it in this presentation. So this tool, this conceptual tool, helps stepping forth micro and nanotechnologies in the frame of 6G, because it helps understand why a sort of reformulation of the concept of hardware is needed. And it also sketches, as I was saying, the pivotal role of MEMS and NEMS in this scenario. So the I2D model methodology has basically three dimensions, three conceptual dimensions, which are identifying, defining, and deriving, identifying, let's say, spotting critical mega requirements, technology mega trends, and forecasted functional features. Now we'll see more in details what these classes of items are. So starting from the very high level, so from the application level, critical mega requirements are high-level needs and KPIs that are more and more central in the transition to 6G and future networks. Moving more towards technologies and let's say hardware software systems, technology megatrends will be let's say segments of the infrastructure driven by the previous mentioned from CMR, so driven by the high-level mega requirements, while in the end forecasted functional features are basically functionalities and characteristics that will be crucial at the low complexity hardware level to enable what is let's say what is above, so basically the systems and the infrastructure. And this 3F basically closes the loop to micro technologies and nanotechnologies. So just to mention a few relevant CMR and TMT in this slide, as they are taken from the book. The CMR1 is volume of data over the network. So this is quite crucial because the estimate says that if you look at the transition from 2020 to 2025, the increase of traveling data over the network will be from 64 to 170 zettabyte. So we are, let's say, just to mention, 1 zettabyte is 1 billion terabyte. Then CMR2 is centralization versus distribution of intelligence, which is somehow linked to what I was mentioning before. And also in this case, there are some estimates which forecast the increase of devices, million of devices per square kilometer of network devices, from 0.1 to 10 million from 4G to 6G. So this means having something like 10 devices connected to the network per square meter, which is huge. Then concerning technology megatrends, so stepping a bit towards the physical infrastructure and key enabling technologies, one crucial aspect to enable this edge intelligence and this distribution of data will be the efficient storage and availability of energy. So it is expected that energy will be necessary at each ramification of the network, and will be, let's say, it will be needed to have it available when needed in the proper amount. Also, incorporation of intelligence at the low complexity device level will be crucial. And this is also something which takes us closer to the micro and nanotechnologies. So finally, the forecasted functionalities are basically closing the loop to micro and nanotechnologies and putting together all these high-level KPIs and the trends. What we can expect to be crucial in the future at the very low complexity hardware level is to have these sets of functionalities here. The one identified in the book are 7, but of course this is just, let's say, a first sketching of this tool. They can be extended. Just to mention a couple of them, also in line with what Kader was mentioning before about CMC, multifunctional in-package integrated hardware device will be crucial, as well as miniaturized devices for harvesting of energy and for storage and delivery of energy. This brings me to the last conceptual tool before starting to review some practical examples. And this leads to the definition of the WIFM ecosystem. So putting together what was discussed up to here, let's say that the transition from 5G to 6G will step from the softwareization of network functionalities, which is something very successful in the 5G scenario, to the so-called intelligentization of the network. So to the incorporation of intelligence in the network in such a way that it is able to self-react to some conditions and ensure the maintenance of KPIs and of the network specifications. This is what actually brings to the need for a sort of reformulation of the concept of hardware, at least at the edge of the network. And this reformulation is expected to step through the increase of separation and symmetry of hardware and software. Separation means to have, let's say, to step a bit far away from what the classical co-design approach is doing. today. So having rather than very vertical and well optimized hardware software systems, which of course can be reconfigurable, can have a lot of functionalities, but they are fixed to a certain application domain, more separation will mean to have hardware and software modules which can combine together more, let's say, more flexibly, probably losing some optimization, but being more flexible in terms of applications and function that they can realize. And this brings also to an increase of symmetry between hardware and software. Symmetry means that actually if now the software is the part which is more flexible and more able to react to some specific condition, in the future, the hardware will start to incorporate some intelligent functions like the capacity to self-react, self-repair, and self-reconfigure to some specific conditions. So to this end, the WIFM ecosystem was conceived as, let's say, a reformulation of the concept of hardware, which makes a parallel with the four elements in nature. So basically, the idea here is to associate some expected functionalities and characteristic of hardware with corresponding element in nature, which can be fire, water, and so on. In particular, this is the definition of the classes of characteristics and functionality in the WIFM ecosystem. So basically, air is the standard concept of software, while Earth is, let's say, a grouping of standard technologies with a particular focus on micro and nanotechnologies. So is what is currently existing. So the novel functionalities are more embodied in the water and fire definition, because water groups devices and a cluster of devices which are able to mix functionalities and, as we will see before, also to have unprecedented capacities in terms of resident intelligence and capacity to react. And of course, water, which identify hardware components, will also interact with software. So some functionalities typical of software are expected to be incorporated into the hardware. On the other hand, fire groups devices and miniaturized components which are devoted to converting, storing, and providing energy. So harvesters, batteries, and so on. Okay, now I step to some, let's say, something which is closer to previous current and future research, because let's say leveraging on all these definitions, I now review some classes of devices which are taken from the literature. So these are all examples already existing in the scientific literature, and actually not developed, not necessarily developed for 6G purposes. Some of them are even quite old, but they are example of miniaturized devices which are already incorporating some of these functionalities which will be expected to be crucial for 6G and future networks. So if we start from water, air, so interaction between hardware and software, as I mentioned, materials and devices with self-healing properties are expected to be crucial. Also, capitalizing on the easy of integration of micro and nanotechnologies, monolithic devices with sensors and components able to address diversified functionalities, which will be crucial. And then still focusing on the interaction of hardware and software, logic circuits, memories, and devices which can enable, for example, computing in memory paradigm will be crucial. And of course, as I mentioned, energy harvesters and devices like these will be also crucial. So now, to start with some practical examples, in the literature there are already some nanomaterial based and let's say micro devices which are able to self heal to some malfunctioning. For example, this work here that you can see in the bottom part of the slide refers to dielectric materials which are subjected to very large electric fields. And the problem of these materials is that when there are some voids, some imperfection in the materials, being subjected to such a prolonged stress leads to the treeing, so to the creation and propagation of cracks through the material until when they reach the breakdown, and so basically fail to work. This work here actually embodies some sort of small reservoirs with a healing agent which are embedded in the material. So when cracks start to develop, at a certain point the reservoir is reached and the healing material is actually filling the cracks and stopping their propagation. Also here, carbon nanotubes materials are used to recover electromagnetic interference shielding properties of material which is intentionally damaged. And in this case, actually, the recovery is triggered by temperature. So just heating the device is possible to start this and trigger this self-healing property. So without spending too much time, these thin films with self-recovery capabilities are also discussed for recovering mechanical properties when some cracks and some cuttings are intentionally, let's say, brought to the device. Still discussing self-healing properties, this example here, which is more recent, is about an elastometer. Where actually a waveguide for a light signal is intentionally damaged. And so basically this device has a twofold resilient mechanism, because on one hand, the resilience of propagation of light within the guide is exploited. So this is somehow already starting, let's say, making possible to overcome the problem of mechanical damages. And then the material is also self-repairing somehow with similar properties compared to the previous work that I mentioned. And so it makes possible to keep let's say an acceptable working condition of the sensor even when it is damaged, physically damaged. Then moving to the water class of devices, monolithic integration of diversified sensors is a good way to have more, let's say, flexible, intelligent devices. This example here discusses the integration of different sensors, 5 sensors that you can see mentioned here within a unique monolithic fabrication approach. Also combining different type of transduction. So we have capacitive, piezoelectric, and resistive transduction within a unique monolithic, multifunctional and multi-device sensing platform. Then stepping to interaction with software, as I said, MEMS and NEMS are quite suitable also to implement miniaturized, let's say, logic gates. Most of them available in the literature are leveraging the mechanical resonance in order to add signals and have an elaboration of such signals. And this is just one of the many works that are available in the literature. And this is also combined to the possibility to have very small miniaturized memory units done with MEMS and NEMS. Here, in particular, electrostatic switches in the micro and nano domains are studied in order to store information, and also this work makes an advancement compared to the classical operation of these switches, because in order to make them bistable, to make the both states of 0 and 1 information stable, a certain amount of charge is injected in the dielectric layer underneath the movable membrane. In this way, actually, the pull-in, pull-out hysteretic behavior is centered around the 0 voltage. So this makes the device bistable, meaning that actually you don't need to spend any energy, to use any energy to keep the information. Energy is required just when the device has to be programmed, so when its state has to be changed from 0 to 1 or vice versa. Then moving on, let's say, 5 classes of devices. Micro and nanotechnology makes possible to realize a wide variety of energy harvesters, addressing environmental sources like mechanical vibration, heat and thermal gradients, light and electromagnetic waves. Then, of course, another interesting part of research is the one of wireless power and transfer systems, where actually energy is intentionally, let's say, broadcasted through, let's say, an electromagnetic coupling between a source where it is available and a target where it is needed. And then, of course, also the miniaturization of batteries is very interesting from this point of view. What in fact is even more interesting is the possibility also here to integrate more devices devoted to energy within a monolithic device, like it is reported in this work, where actually both the solar cell, so the light energy conversion, and the thermoelectric energy conversion is combined in a unique device. And just to mention, let's say, still stepping forth in this discussion, another very interesting part of devices which could be crucial to enable, let's say, edge intelligence and all these fancy features of future networks, is the possibility to have self-powered device. So still focusing on energy, it is very intriguing to have the harvesting of energy combined with the normal operation of a sensor. This is an interesting contribution in this direction, because here an inertial sensor, an accelerometer, is discussed, and this is combined also. Basically, this accelerometer exploits piezoelectric conversion for sensing acceleration, but it is also provided with a permanent magnet and a coil on the other hand of the movable structure, which makes possible to harvest energy to self-power the sensor. Of course, the device is also equipped with electronics which make possible to have a self-compensation, because as you can imagine, the harvesting part is actually influencing the behavior of the sensing part. So this device is able to, let's say, harvest energy and provide itself the energy needed to operate while operating. And finally, this is a list of Earth technology. So coming back and recalling the definition of the WIFM ecosystem, Earth technologies are actually standard. We can call it standard technology. So in the sense that they don't have that much of combined functionalities and monolithic integration, but they can be the starting point, so the building blocks from which it's possible to think and conceive new MEMS and NEMS devices able to incorporate one of more the features that I mentioned up to now. So monolithic integration, self-resilience, capacity of self-reacting and self-repair, or having simply monolithic devices which are able to realize a wide variety of functionalities. You can see here, let's say this is a partial list. I mentioned RF MEMS, metasurfaces, flexible electronics, also heterostructures, which are not so related to MEMS and NEMS, but are, let's say, quite close from the fabrication point of view. Then, of course, integration packaging through device fusion, additive manufacturing, which is also an interesting and a rising field of research, photonic and quantum technologies. This brings me to the last part of the presentation, where actually I want to spend a bit more technical focus on RF MEMS, which is actually what I'm mainly researching here in my institution. So let's say RF MEMS is classified as an Earth-like technology. So let's say this is what actually we did through the years. We realized a wide variety of both of lumped components like microswitches, variable capacitors, and inductors, as well as complex networks like tunable matching tuners, reconfigurable resonators, filters, phase shifters, and power dividers. Okay, so now bringing this discussion into the frame of beyond 5G, 6G, and future applications, it must be stressed that actually there is a lot of interest currently on massive MIMO, so on multi-element antenna, enabling advanced beamforming for small and picocells. So for towers, radio towers, which are working at quite high frequencies and which are serving with very high throughput mobile or fixed end users. These antennas, of course, are high order antennas, so they are arrays of elements, of radiating elements, which have to, let's say, interfere with each other in order to steer the broadcasted beam. And they need actually quite complex networks to be physical networks, let's say hardware devices, to be properly driven. This is a scheme of an antenna, of a massive MIMO antenna, and of the receiver. So let's say that in a most general case, each element of the antenna needs to be connected to what is called here passive control unit. So to a circuit where actually a tunable power attenuator is included, along with a delay line, tunable delay line, and of course a switching unit in order to switch the antenna from transmission to reception in case both are addressed. Of course, the fact that the application frequency will increase up to even 100, 300 gigahertz makes everything more difficult, because we need more integration, more, let's say, more pronounced performances in terms of low losses, low power consumption, and so on for this hardware. So basically, matching this application with RF MEMS, what we did, and actually what is quite common to be seen in the literature, is a lot of discussion about RF MEMS based components like power attenuators, phase shifters and switching units. And this makes actually RF MEMS technology a Earth-like technology in the frame of the WISM ecosystem. But in fact, MEMS are characterized also by their high capacity in terms of integration, of redundancy, and of complexity in the design which can be realized. So one option will be the one of realizing monolithically, so in a unique piece of silicon, a PCU, a passive control unit for this type of application. So instead of having single components and separated, let's say, discrete components made in other technologies or even in RF MEMS technology, what can be a turning point for this type of application is to integrate the whole design of reconfigurable power attenuator, delay line, switching unit within a unique chip. Then, of course, improving the performances, reducing losses, reducing also the cost, the integration, and the miniaturization, of course, of this type of devices. So this is how, finally, how RF MEMS technology can be, let's say, a building block in this vision, which actually can enable unprecedented functionalities and possibilities. Of course, this is just a focus on something I'm working on. The same consideration are valid for all the other technologies that I mentioned before and that I reported, referring to the scientific literature. Okay, so this brings me to the conclusion of the webinar. There is just one last item that I want to mention that I was discussing also with Kader before we began this presentation. Is that actually next year we will be hosting a topical workshop on these topics, on most of the topics that I presented to you in this webinar. The event will be supported and sponsored by the Transducer Research Foundation in the United States, and will be held, as I said, in our institution, in Fondazione Bruno Kessler in Italy, in April 2025. This is, let's say, a tentative list of the topics that will be covered during this topical workshop. So if you are interested, please stay tuned, as we'll be releasing later on an official website and also more details about the holding of this event. Okay, the conclusions are quite obvious, so let's say I just skip them to save some time. And with this, I conclude my presentation, and I'm open for questions. Thanks for your attention.